Okay, so in this case, we need to prove the sum of a geometric sequence or a geometric series, okay? So we know that that formula is given as Sn is equal to A into 1 minus Rn over 1 minus R. Alternatively, this formula could also be given as, okay, something like Sn is equal to A into Rn minus 1 over R minus 1, okay? So we're just gonna prove just the first one, okay? And then we can probably translate into the second formula. All right, so one thing we need to know is that any geometric sequence or series will be given or written as A as the first term, and then we have AR as the second term, then we have AR squared, and then we have AR cubed, and so on and so forth, up until the last term, which will be given as AR n minus 1, okay? Which means the second last will be AR n minus 2, and so on and so forth, okay? So I'm just gonna use this to start with the proof. Okay, so I'll say that the sum of the series will be A plus the second term, which is AR, then the third term, which is AR squared, plus I can skip some terms there, and then I just write only the last two terms, okay? The last term, which is the Tn, will be AR n minus 1. All right, then what I'll do, I'll get the first equation or the first expression, this is like equation 1, and then I'll multiply it through by R. I mean, every term should be multiplied by R. So if on the left-hand side, I'll have R with Sn, and then in this case, I'll have AR, and then I'll have AR squared, then I'll have AR cubed, and so on and so forth. And then I'm gonna be left with AR to the n minus 1, and then I'll have AR to the n as my last term now, if I multiply through by R. Now, if this is our equation number 2, whenever we're dealing with a sum of a geometric, we have to subtract equation 1 and equation number 2. So what I'll have, it will be Sn minus Rsn. Okay, this is equal to, now if I subtract, remember this A does not have anything common for the second equation, so the A will just remain. And then what I'm observing is that this is gonna cancel with that. This is gonna cancel with that. The AR3 will cancel with that, and so on and so forth, and to continue to a point that even this ARn minus 2 will cancel with whatever is meant to appear here. Then this will also cancel with that. So in other words, everything is gonna cancel out. I'll only be left with this A and then this AR to the N. So since the subtraction, I'll say minus AR to the N. And then my next step should be the factorization. Take out what is common. So Sn is common there. I'll have 1 minus R. And then on my right-hand side, the A is common. I'll have 1 minus R to the N. And then divide both sides by this bracket. So our Sn is going to be A into 1 minus R to the N over 1 minus R. So this is the formula as requested, okay? And so this only works in most cases if R is greater than, is that greater than or less? It's less than 1. Okay, so if our R is less than 1, that's when we can use this formula. Now, for you to get this other format where the Rn comes first, you'll have to get equation 2 and then subtract equation 1. Okay, so if you get equation 2 minus equation 1, okay, so it's gonna be like Rsn minus Sn, okay, Rsn minus Sn. And then remember, we're just canceling everything, canceling. So remember, if this equation is on top, then this Arn is gonna be positive. Okay, so I'll be left with Arn minus A. Then what happens? Factorization, take out the Sn. I'll have R minus 1. And then on my right-hand side, A, I'll have Rn minus 1. Then divide both sides by the R minus 1, then over R minus 1. So this cancels that, and then the formula just comes out the way it is. So this, in most cases, can be used when R is greater than 1. But regardless of which formula you use, for as long as the substitution is done correctly when you're doing the application, you'll always end up with the same answers. All right, thank you very much. We'll stop there.